Hello everyone, today we are going to solve a Leetcode problem on trees. The problem is count complete tree nodes, and this is a really interesting problem. So let us read the problem statement. And given the root of complete binary tree, return the number of nodes in the tree. And the definition of complete binary tree is that according to Wikipedia, every level except possibly the last is completely filled in a complete binary tree, and all the nodes in the last level are as far left as possible. So, what is a complete binary tree? So let us see. A complete binary tree is a binary tree that is all the levels. If we see, all the levels are completely filled except possibly the last. So if I have a tree like this is a complete binary tree. But if I have a node that is like this, but I do not have a node in here, that means it is not complete, because all the levels up to this point are complete though, but in the last level the nodes are not as far left as possible, right? Because this particular node is missing, and this is also not complete. And if we see like this, if the node if a tree is like this, so this is like all the nodes have 0 or 2 children. That means it is every node is balanced, but this is not complete binary tree, because in the last level this all the nodes should be at as far left as possible. That is, the left should be filled first, then only the rightmost nodes at a particular level should be there. Okay, so I hope you understood what a complete binary tree is. And a good example of complete binary tree is a heap. Heap is a complete binary tree. Okay, and we have to design an algorithm that runs less than big O and time complexity. Okay, and the constraints are that the number of nodes are in the range 0 to 5 into 10 to the power 4, and node value is also in the same range, and it is given that tree is guaranteed to be complete. Okay, so let's see how we are going to do that. The task is that we have to count the number of nodes in that complete binary tree. So if we consider this example, 1 2 3 4 5 6 7 8 9 10 11, like this, then how we can count the number of nodes? So the first approach that comes to our mind is traversal. So we can use either BFS or DFS, both are fine, but the time complexity of both the solutions is big O of n, and we have to reduce the time complexity somewhere, like we have to reduce it by either so what can be the possible smaller time complexity than n? It can be in terms of log n something. So let us see how we are going to do that. Although the solution that optimal solution for this is log n square solution. So we are going to see how we are going to optimize this. Okay, so if we are at a node and we try to find the left height of the node and the rightmost height of the node. So leftmost element is 8, and we will get 3 from the leftmost height and 2 from the rightmost height. So what we are going to say, if there is a mismatch in left and right height, then we are not sure that by how much, that simply means that the last level is not completely filled. That means we are not sure that by how much the last level is filled, but we are sure that up till this point it will be filled, but it is of no use for us right now. So we are going, what we are going to do, we will simply say that add 1 for this particular node and get the count for 2 and 3, that is the children of this one. So we will simply say count for 2 and 3, whatever the count for 2 and 3 is there, we will simply add 1 to that and return, right? So count is going to be a recursive function here. So at 3 we get 1 in the left and 1 in the right. So there is a match, like all the elements are at height 1. So we can simply use a formula. So if there is, let us say, left and right height are let us assume 5, then what is the number of elements that are going to be there in that subtree? That is going to be 2 raised to power height minus 1. So this is going to be the number of elements in that particular subtree. And if you see, this is the optimization here. We did not traverse any of the internal nodes, right? We only traverse the nodes that are there at the edges of the tree, like leftmost and the rightmost. So internal nodes are skipped. This is the optimization, and we will see how the time complexity is log square n. We will come to that point. So now here we will get 2 raised to power 2 minus 1, that is 3. So 3 is going to be the number of nodes here. So we will get 3 here, and at this point we will get 2 in the left and 2 in the right. So that means we will get 2 raised to power 3, and that this is going to be 2 raised to power h plus 1 if we are counting this one as 0, then 1, then 2. Then we are getting 2 raised to power 3 minus 1, that is going to be 7. So the number of nodes in here are 7. So if you see, we skipped these 2 nodes, but as the tree grows larger, then we can see this approach working effectively. So the answer will be 7 to 10 plus 1, 11. So 11 is going to be our output, and if we count this, there are exactly 11 nodes, right? So now let us first implement this solution, and later on we will try to see how the time complexity is log square n. So it is given in the example that height can be 0, number of nodes can be 0 as well. So I will simply check it here. If not root, then simply return 0. Else what we are going to say, we need to count the left and right height. So left is going to be count left height is going to be one function that is going to give us the left height of the node, and we are going to count right height as well. After getting the left and right height, we will simply compare. If left height is equal to the right height, then we will do something else. We will return 1 plus count nodes in the left of the root, that is both the children. We will simply count for both of the children. It should be count nodes. Okay, let me correct it here. And in case there is left is equal to right, then we will return 2 raised to power whatever the height is, left plus 1 minus 1, that is 2 raised to power h plus 1 minus 1. And here we will make the function for count left height, and we will pass node here. If not node, then return 0, else return 1 plus nodes left. It should be a function count left height nodes left, and we will make another function int count right height, that is going to be tree nodes star node, and if not node, then we will simply return 0, else we will return 1 plus count right height nodes right. So we made the functions for counting left and right height. After getting left and right height, we are simply checking if left is equal to right, and we are returning 1 to raised to power left height plus 1. Okay, and height should be 0 base for this, but in this case, if there is one node, then also we are getting 1, so that means we do not need to add 1 here, because if we see we used 0 1 2, like 0 based height here, that is the level height levels. Here we are using height, so we can simply use 1 raised to power 2 raised to power height minus 1. Okay, I think this is it. Let us run it. Perfect. Okay, let me submit it. Okay, it is working fine. So let us talk about the time complexity, why it is log n square. So if we see what we are doing at particular node, we are counting height, right? And for counting height, we are just counting left and rightmost height. So let us assume that both of them take 2 log n, right? And we can simply remove this 2 for now. We can roughly say log n time, right? So log n time we are taking to count the height at a particular node. And how many times are we counting the height? So if the tree is really large, then in that particular case, at least half of the time we are just using the formula. Like if we, let us say we are here, then if we divide this tree in 2 parts, then this part is balanced, either this part will be balanced or this part. See, if the nodes are filled up to this point, let us say up to this point, that means this part of the tree will be balanced. So we will not be calling for this particular subtree, but this part of the tree is going to be unbalanced, so we will be calling it for one more time. So at this point we will again see that this is balanced, this subtree is balanced. So if we see, we are just calling half of the times, not for all the nodes, and we are just going down by the height every time. So we are calling this count height function logn times. That is the height of the tree. So logn times logn, that makes the solution logn square. So I hope you understood my explanation. If you have still any doubt, you can ask in the comment section. And that's it for today's video. Thank you for watching. See you in the next one.